Alright, so we started this yesterday. We were looking at the distance of a falling object, and I want to get into this and kind of get to the point of what we're doing with this, and then use that to get into our discussion of derivatives here. How much time did it take for the ball to hit the floor? 0.729 seconds. Okay. Now, what you guys just found with that is you found a point. According to our function, you found the point 0.729 negative 8.5, because the ball is falling down 8.5 feet. Okay, it's going to take that long in a free fall to hit the ground. Okay, so I had you find 3 other points. So what were some of the points you guys came up with?
4, 6 something, then 10.
What?
Like 4 feet off the ground, 6 feet off the ground.
0.5.
Wait, having fallen 4 feet or 4 feet off the ground?
After falling 4 feet.
Okay, and what was your time there? 0.5? Okay.
Yeah, 0.5.
And then what's another point that you guys found?
-4, 0.5. That's way too
No. -4 would be -4 seconds.
Yeah, I realized that first.
Okay, so 0.5, -4.
0.25, -1.
Okay, 0.25, -1. And how about one other one?
0.661 -7.
Right?
Okay.
That's feet off the ground, right?
Oh, we just chose to.
Well, no, think about our formula here. This is the distance that it has fallen. Okay? The distance of an object falling. So how far has it fallen? So at -1, it's still 7.5 feet off the ground in this case. At -4, it's 4.5 feet off the ground. At -7, it's only 1.5 feet off the ground at this point. Okay? So, question here, just based off of what you know, what should be the fastest of all these speeds? If we take the average, we found the average speed between this point and the point where it hits the ground.
The higher the distance.
Okay, yeah. The closer it gets to the ground, the faster it's going to be going, right? I mean, that makes sense, because gravity is pushing it faster and faster. Okay. So how would I find our average speed from, say, this last point here to where it hits the ground? How do you find speed or velocity?
Distance over time.
Okay, so how far does it go from here to the ground?
7 over 0.661.
No.
1.5.
You're doing average velocity from when it started to drop to where it is now. We want average velocity from where it is now to where it hits the ground. Okay? What?
Well, the distance is 0.68.
Find
The time difference is 0.68.
Oh, the time difference is, okay. So the time difference is 0.68 seconds.
And the difference between the two.
Wait, is it 0.068?
Yeah.
There you go.
So when it hits the ground, it's going at a speed of 0.72%.
No.
No, that's the time.
When it hits the ground, that's 7.29 seconds after we dropped it.
Oh, okay.
Okay, this is time, this is how far it's fallen.
Uh-huh.
Okay? So, how far does it fall in this 0.068 seconds?
1.5.
Yeah, 1.5, and technically a minus 1.5 since it's falling downward, right? So what's our velocity here? 22.06 feet per second, right? Right? Okay. Now let's do, for sake of time, let's just do one of these other ones. Let's do the 0.5 and the -4. Okay? So our velocity on this one would be what?
Even like in the first.
For this one. Yeah, for this one. What's our...
Well, on the top, it's -4.5.
Okay, it fell another 4.5 feet. In how long?
0.229.
There you go, 0.229. So our velocity there, if you divide, our velocity ends up being what, -19.65
0.65.
feet per second, right?
99.7.
Now, what's happening to the speed as the point you choose gets closer to the ground? As the ball gets closer to the ground, what's happening to its speed? It's getting faster, okay? So the average velocity, remember we said we're finding the average speed or average velocity when we're doing this, okay? So, just thinking in terms of the situation, it makes sense that, hey, if we take the average velocity from 4 feet off the ground until it hits the ground, that's going to be a little slower than if we take it from 1.5 feet off the ground to when it hits the ground, okay? Because it's sped up by then, all right? Now think about how we found velocity, okay? This -1.5 is what?
Distance is the difference.
Okay, it's the difference of your distances, right?
It's delta D and over delta T.
Okay, good. Delta D over delta T. The change in your distances over the change in your times. Okay? So let's think about this. What are we actually finding, or what formula are we actually using when we're finding the speed?
Slope.
It's slope. Okay? We're finding the slope. All right, and to illustrate this, okay, think about your distances, all right, as time goes on. You know, it's getting smaller and smaller and smaller and smaller. That's going to be somewhat parabolic, right? If we kind of took a time-lapse photograph of this happening, you know, here's the ball at 8.5 feet, and then here's at, 4.5 feet off the ground. Here it is at only 1.5 feet off the ground, and then here it's hitting the ground. Okay? It's parabolic. And what we're doing, if you think about this, I'll zoom in. If you think about it, what we did when we found the average velocity, if we were to go from the very beginning when we dropped it to the end, that's actually 11.7 feet per second. Okay? So that's minus 11.7 feet per second. Okay? If I were to find, or we did find this slope right here, okay, that was at the 0.5, -4. What did that velocity end up being? Was it negative 19.65? Okay. And then on this last one that we just did, let's use blue. This last one here was at that -7, and it was like, what was it, like a 0.6 something? 0.661. Okay. And what did we get for the velocity in that case?
22.06.
22.06. Now, question here. Which of these do you think is the closest to the velocity that the ball is going when it actually hits the ground?
The last last one.
Yeah, negative 22.
Yeah, okay. So in other words, what if I wanted an even more accurate estimate of the velocity here?
You do like negative 8.49.
Okay, yeah, I could do like negative 8.49. Or just getting closer and closer and closer. And if something's getting closer and closer and closer, what concept are we going to think about? Limits. Okay? Limits.
Oh, I see what you did.
Okay? Yeah, so we've been talking about limits here. Now I want to introduce the concept and then come back to this idea of a limit and the idea of the slope to address what we're finding, okay? Oops. What we've been trying to discover here is the rate of change, or in this case velocity, at a specific point on a graph. Okay? And what this is, we're good here. Alright, so our basic concept's the derivative. It's the rate of change, and you'll see here, we're talking about tangent lines. Alright, I have a tangent line to this curve here. Alright, the thing that makes things curve is the fact that their slopes are changing. Alright, back when you learned about lines in algebra, you learned that, the lines are straight because they have a constant slope. Alright, guess what? If you take the derivative of a linear function, guess what you're going to get?
Curve.
No.
0?
No, it's just one number.
It's just a constant, right? Because the slope of a line is constant, okay? That's
I
alright.
got that. Sorry, I was not.
That's alright. So, that's what makes a line straight, is that the derivative is constant. The slope is constant. Here, though, we have this curve, and if you draw the tangent lines at different points, you can see here that our rate of change is going to be different, okay? Now, the point that we're looking at is the point of tangency, alright? And here's our tangent line. If we find the derivative at that point of tangency, that's going to give us the slope of the tangent line, which is also the rate of change at that point, okay? One reason why this is significant is, take for example motion. You know, if in space travel they use tangents a lot, okay? You'll have, a satellite orbiting, they want to shoot a satellite out towards some planet somewhere. So what they'll do initially is they'll have the satellite kind of orbiting the Earth. Alright? Now this is a very simplified version of what they do. But here it is in its orbit. And if the target that they want to hit is way out here, okay, they've got to figure out where they're going to go so that the tangent line will actually hit this target. Okay, now that target isn't necessarily where the planet is right now, it's where the planet's going to be like 3 years from now when the satellite actually gets there, which is mind-blowing to think about, that they can predict that. But you go like this, and hopefully get a tangent, okay? But this can help us figure out when we have to release, alright? So we need to get our satellite to shoot out of the Earth's orbit and slingshot out at this point in order to hit our target. Okay? So we use tangents there a lot, and we can use the velocity at that tangent and whatnot, or the rate of change at that tangent or at that point to help us figure it out as well. Okay? Now, a little bit of terminology and notation here that you really need to be familiar with. Okay? Differentiation is simply the process of finding the derivative. Okay? If they say to differentiate this function, they're just telling you to find the derivative. If something is differentiable, it's something that we're able to take the derivative of. Okay? And then there's different notation here. Okay? Here you have this f apostrophe of x. That's f prime of x. And And then you also have this notation here, dy dx. Okay? And you'd write it as a fraction, really, dy dx. If you know what y is. If you have some other random function that isn't necessarily named, you could also use notation like this. The derivative of, with respect to x of the function, say, x squared plus 3x minus 5. Okay? That would say the same thing as if you had said, hey, y equals x squared plus 3x minus 5, and then you write dy dx. Okay, so that notation there is something you need to be familiar with, and we use both types of notation, the primes and the dy dx. Okay? In fact, IB even tends to use more of this dy dx notation.
Why does it say d over dx then?
Y is a function, right?
Also, you put the
So,
function on the side.
if we haven't named the function yet, then we can just say the derivative of this with respect to x.
Okay.
Alright, so let's take and develop this concept and develop the idea of a derivative. We said we were using slope, okay? So we have here the slope formula. We have two different points, and there's some extra dots in there because it didn't export right, but you can get the idea here. We have 2 points. We have x, f of x. That's the point that we actually want to find the derivative at. Okay, so this point right here. So we've picked some point on our graph, and we've now drawn a secant line through that. Okay? Remember, a tangent line intersects a function at only one point. That's this line. We've now drawn a secant line between these 2 points. Okay? Now, the notation that we're using here, you'll see we have a plus delta x. Okay? And that's because I don't want this to be a set amount that we are changing where this other point is. I just want to have some random amount here of delta x, okay? Now, if I move my x over this much, then I have to find the y-coordinate by evaluating at this new value of x, okay? So here's a new point right here at x plus delta x, f of x plus delta x, all right? And you guys can see the slope, as always, is delta y over delta x, okay? But let's rewrite this slope in terms of the point that we've got here, okay? So, let's do our slope formula. We have the change in y's, so we have f of x plus delta x minus the original y-coordinate, f of x, right? There's our delta y, the change in our y-coordinates. And that's going to be over x plus delta x minus x. So there's the change in our x's. Alright, so if you think about this, the slope, we just found the slope of the secant line. It's f of x plus delta x minus f of x all over, notice the x's cancel out in the denominator, delta x. Okay? So that's what our slope will equal at any given point. Okay? From the point that we want the derivative at, there in black, okay? So this point right here, to any given point, any given secant point. Okay? Now, what we're doing here, and this is what we saw with our falling ball, is that if we move this point closer and closer and closer, to the point where we want to find the derivative, okay? Here's that point we want the derivative at. And I'm going to have to clean up this drawing a little bit. Alright, so that's going to be f of x. Let me get rid of some of these extra.
There's so many little dots.
How can you clean it up?
Draw all over the whiteboard.
I'm just drawing over it with white.
Oh.
Yeah. So, okay, so let me get some blue in here.
Yeah.
Alright, so here's our delta x going over to this point. Okay, and there's our blue point. Let's put our green point back on here. Okay. And I've drawn in tangent lines each time. Now, as we saw with the ball, okay, which of these points is going to give us, of the three that you see here, which of those is going to give us the closest approximation of the velocity right at the point x f of x? Yeah, the blue one, because it's the closest of those three. Okay, so if you think about this, I want to keep moving this closer and closer and closer. So what's going to happen here as I do that? What's happening to delta x as I move that point closer and closer and closer? It's getting smaller. So delta x is actually approaching... Delta x is approaching 0. That's right. Okay? Delta x is approaching 0. So guess what? If I want the derivative at a specific point, what do I need to do? If I want to find the slope at that specific point,
Take the derivative at that point.
How is delta x?
Find the limit as it approaches 0.
yes, but wait, what'd you say?
Find the limit as x approaches 0.
We're finding the limit as this delta x approaches 0, and that is what the derivative is, okay? You'll see here that the limit as delta x approaches 0 of that slope that we were just looking at is the derivative.
Wait, how is x approaching 0? Delta x.
Delta x is approaching 0 because notice here, as I move this point closer and closer and closer along the graph to the point that I want, this difference in x is getting smaller and smaller and smaller, and it's going to, as we keep picking points closer and closer, that delta x is going to get smaller and smaller and smaller. If we take the limit as delta x approaches 0, then that will actually give us the slope at that specific point, and that's what the definition derivative is, okay?
But you can't just do substitution.
We cannot, because we're going to get 0 over 0, okay? Now let's talk about that here, okay? By the way, one other name for this that IB uses a lot is, they say, find the derivative from first principles. Okay? From first principles. And basically they're just saying use this formula. This formula is on your formula booklet. Okay? The only difference, I can't remember off the top of my head, they might use h instead of delta x. Sometimes they do that just to simplify.
Just to mess with
You'll see it both ways depending on if you look online or something like that. You'll see it written both ways all the time. Alright, so